Hey everybody, okay, we're going to do a quick recording just for the derivation of this is the nth bright line basically of a diffraction pattern. So it's the n lambda is equal to d is equal to d sine of theta. Okay, so this has very little maths in it, but what it does, it just means that you have to really understand what's going on. So I'm going to look at these. These are two waves here, and we're going to say that they're coherent. So they have the same wavelength and the same thing, and they're in line. So this peak is lining up with this peak, and that peak is with that. And the troughs, they should be. My pictures aren't great, but they should be. We'll pretend that they're coming down here, and they're all matching up. So all these peaks should be matching up with each other, and they should all have the same wavelength and the same frequency. Okay, and what are we going to have? Well, if we know if we add these together, well, what are we going to get? Well, we're going to get just a wave where we add all of the amplitude. So to add any two wave, you just add the amplitude of this one to the amplitude of this one at every single point, and what we'd see is that it would get double the height, and it would still have the same wavelength and same frequency, but it would just be double the height. So that's if we add those, okay? And this is what is constructive interference. Okay, so now equally we have other options, okay? So what happens if we say move this? Say these were coming from a laser or something, and they were sources, and we had two lasers, and I've shifted one a little bit. Now look, I've shifted one there now half a thing, so we can see that this peak is now going to line up with this trough and this with this, and if we then added them together, well, what would we get? Well, we'd get nothing. Okay, if we added them both together, because this plus one, say this maximum amplitude would be at this maximum amplitude in the other direction, and so on, and so these would just add up to be zero, and there would be nothing there. Okay, so we can see as I shift this, as I move one of these, the sources of these, as the wave has to travel further, it goes out of phase is what we say, okay? And here it'll be complete destructive interference, but if I keep shifting it again, you'll see that those blue lines will line up again, okay? And now we're going to have peaks to peaks again, and so again we're going to have like our maximum constructive interference at this point. And what can we say about this? Well, we can say, how far have I moved it? Well, if you look, I've actually moved this at exactly one wavelength. So if we have the maximum constructive interference here, and if I move it one wavelength forward, we're going to have another, and you can see I can do that again. I can move it one wavelength forward again, and I'll have another maximum. So we can see that every time there's a path difference. So the distance between, say, the source of this, or the distance it has to travel, is an integer number of the wavelength, because it'll work backwards as well the other way, won't it? That's still all lining up. An integer wavelength, so of lambda, which is just the wavelength, then we're going to have constructive interference. So if I have a path length of n lambda, this is where n is any integer, and lambda is just the wavelength, then we're going to have the maximum constructive interference. Okay, so that point's important, and once you really sort of understand that, the rest of this derivation should be super easy. So I'm just going to move this up for a second, and we're going to look at our diffraction grating. Okay, so this is for the nth term. So this is n lambda is equal to d sine of theta is what we're going to derive now. Okay, so what we've got, well, let's have a diffraction grating. Okay, I'm only going to draw 3 holes in this, say. Okay, so there's our little diffraction grating, and these are little holes. And now we know that the spacing between the diffractions, so we're just going to do it center to center, but you can do it top to top or bottom to bottom, it doesn't matter. That between all of these, let's say, and that one to there as well, all this distance is all just going to be d. Okay, that's just the grating constant, or the separation between each of the gaps. So that's center to center, or top to top, bottom to bottom, it doesn't matter what you choose. But now say we have a light ray coming in here. Hold on, we'll use blue. And this light ray is coming in here, and they're coming from this. They're coming into each of these, 3 of these. Okay, and then it diffracts. and goes off in an angle, and so they'll all diffract at this. So what we have, this is our rays coming in. This is usually by a coherent source, otherwise this won't really work, so that's why we usually use lasers. Okay, there's our light coming in, coming out of the diffraction pattern. Now this is what we have here. So what we're going to do, you know me, and we always love triangles, don't we? So I'm going to make a little right angle triangle, say coming off this part. I'm going to draw one in there, so that'll be a right angle triangle. Yeah, and so equally, this should be exactly the same as this one here. Okay, because these are all parallel lines. And we can look. Now, we've just made this little triangle, and I'm going to bring it out here and draw it in a little bit more detail. So let's just have this triangle out here. So that was D, the grating constant, yeah, and this is where the ray was going to go, and this was the line that I drew just to make it a right angle triangle. Okay, and what we're going to have is this angle is going to be theta here. Okay, and if you look, if you remember your trigonometry, well, if we just had this angle here is going to be exactly the same as that. Now, if you don't believe me, you can work it out knowing your trigonometry rules, but that's exactly the same as this angle. So we just have this little triangle here. Now, so what do we know about it? Well, so we have D and we have theta, so we can use our SOHCAHTOA. Okay. And what we want is we want to find this length. Okay, and so what is that length? Well, we want our opposite here, so we're going to use this sine. So here, we're just going to have sine of theta is equal to the hypotenuse over, or the opposite over the hypotenuse, sorry. The opposite over the hypotenuse. And in this case, we know our hypotenuse is D. So this is just going to be D sine of theta is equal to our opposite. Okay, so our little triangle becomes this. So there's D on that side, D sine of theta here, and theta. Okay, so this is our little triangle. Now, what do we know? Well, if these lights come in, what do we know? If these are going to, say, reach further out here. They're just going to keep going, and they're eventually going to join up at a spot on the wall. Now, I know that's all crooked and stuff, but you get the idea. They're going to join up at some little spot. And what condition do we need for this to have constructive interference? Well, if these path lengths, if there's a difference of anything of a multiple of the wavelength, then we're going to have constructive interference. Okay, so you can see from the difference between this length getting to this point and this one getting to this point, or this is just that little length here, this little bit here that we've marked in our thing. So if this is an integer multiple of a wavelength, then we're going to have constructive interference. And that's all we need to know for this whole derivation. So if that's true, what we can say is we can look at our equation, and we have our little triangle here, and well, D sine of theta, and we want that, if that's any multiple of the wavelength, an integer multiple, well, we know we call that n lambda, and so the equation is just n lambda is equal to D sine of theta. Okay, and that's all it is. This is from our little triangle, and that's the entire derivation. So it's just more about understanding than anything else. And that's it. This is the condition. So as long as this distance here and this distance here, because these should all be parallel, as long as that's some multiple of the wavelength, an integer multiple of the wavelength, then we'll have constructive interference. And we can use this then to find, say, the 10th bright spot or the 3rd or whichever, as long as we're given these. Okay, I hope that helps.